Hello, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with spectroscopy and ultraviolet visible spectra. This is lecture number 14. In this lecture, I will explain you shifts of lambda maxima. Mainly, there are four types of shifts that you can see here. Here, you will see that there are four types of shifts. One, in which this wavelength of substance increase and this graph will move towards a higher wavelength, that is red color, and that is why it is called bathochromic shift or red shift or higher wavelength shift, in which wavelength or lambda maxima will be high because of certain differences. Similarly, another shift is the graph will move, or this high peak will move towards the left side, and that is towards the lower wavelength. So it is called hypsochromic shift or blue shift or lower wavelength shift, in which lambda maxima will be low. So third one is where the height of the graph increase because of the absorbance increased, and that is called hyperchromic shift or higher intensity shift, in which epsilon maxima will be high. Fourth one, in which the height of the graph decreased, and it can be, in that case, absorbance also decreased, which is known as hypochromic shift or lower intensity shift, in which epsilon maxima will be low. Normally, it is observed that along with bathochromic shift, you will observe hyperchromic shift, and along with hypsochromic shift, you will observe hypochromic shift. So now let us take individually each one. So first of all, we will take bathochromic shift. It is also known as red shift. And the reason for that is because the wavelength of the substance, wavelength of this absorption increased. And why it is increasing? There are three reasons for that. So in presence of extended conjugated pi bonds, you will find more resonance, and that's why you may see the shift of the lambda maxima towards the right side. So first is presence of conjugation. So we take two examples in this case. The first one is this one, which is called 1,3-butadiene, or in short butadiene, in which there are two alternate pi bonds. So there will be two conjugations, or this much is a conjugation. Now we'll take another example. In which you will find 1, 2, 3, and 4 pi bonds, and total 10 carbons. So we call it deca 1357 tetraene, or in short decatetraene. Okay. Now both are having conjugated double bonds. So our main system, that is diene system, is this much, in which you will find two alternate pi bonds. Over here also you will find diene system. But in this case you will find extended conjugation of two extra pi bonds. So here there will be two extra pi bonds. So net system will be from second carbon to this 9 carbon. Okay. So let us see how this will change. Here in decatetraene, you will find shifting of pi bonds. Now here double bond will shift over here. So pi bond comes over here. The second pi bond will reach here. Next will be like this. So both are same. This is also deca tetraene with 1357. Okay. So here you will find resonance. Now, due to resonance, electrons revolve or electron move from one end to another, energy decreases. If energy decreases, you know that E is equal to hc upon lambda, and E is inversely proportional to wavelength. So we can say that when lambda or wavelength decreases, wavelength wavelength increases. So absorption will be more in case of deca tetraene, but butadiene is having less absorption, and that is why if you see the graph here, in case of butadiene, the lambda maxima will be about 215 nanometer, while in case of decatetraene, lambda maxima would be about 280 to 285 nanometer. So this way you will find that lambda maxima increases, and therefore if you see the graph of butadiene and decatetraene, there will be slight shifting. So for butadiene, the graph is about here, and lambda maxima would be this one, which is about 215 nanometer. But in case of this is for butadiene, and in case of decatetraene, the graph goes like this. This is for decatetraene, in which lambda maxima would be 280 nanometer. So here the graph goes in the right hand side. So this is called bathochromic shift or red shift. Okay, and that is why, because of conjugation. So if you have a higher conjugation, then you will see the graph will go towards the right side. Similarly, when we see this one, the second reason is the presence of oxochrome. Sometimes oxochrome enhances the color, and that is why wavelength also increases. Let us see this one. Benzene. Its lambda maxima is because about 255 nanometer or 256 nanometer. But when you put NH2 group on top of it, which is a oxochrome, why? Because it is having lone pair of electron, and it is totally saturated. But in this case, you will see that this lone pair of electron will shift, and you will find resonance structures of aniline. Because pi bond electron shift over here, you will find double bond, and then this one, and then pi electron will shift over here, which will produce negative charge, and so on. And you will get so many resonance structures. So here, because of the presence of oxochrome, This will lead to resonance, more resonance structures. This will decrease energy and increase lambda maxima. So this way you will find bathochromic shift in aniline, and because of this lambda maxima is about 280 nanometer. So in aniline the value of lambda maxima is about 280 nanometer. In comparison with benzene, you will see that lambda maxima increases and you will see the red shift because of the presence of oxochrome. And the third reason for chemical shift towards red color is change in polarity of solution. Change in polarity of solution. Change in polarity of solvent. Okay. So how change in polarity of solvent can change the shift? It is observed that if solvent can stabilize anti-bonding molecular orbital of pi, then it is possible that it is observed when solvent can stabilize anti-bonding molecular orbital of pi, which is called pi star, with hydrogen bond in excited state. Then red shift appears. So these are main three reasons for bathochromic shift in any compound. That's it in this lecture. Thank you so much.